Oh my gosh. All right, so let's take a look at, let me share my screen here. We're going to be doing a few last comments on moment of inertia, and then we're going to blast into torque. So let's do that. Okay, so make sure you do this one. This is on the list of required questions that you might be asked about. So make sure you all do that one, both of these. And I think this will lock that in pretty darn solid for a lot of these shapes. Yeah. And keep in mind, if at any point there's something like this one, like I notice right now, part E relates to the perpendicular axis theorem. Anything that has the perpendicular axis theorem, you don't have to worry about. So part E there and probably part E here. All right. So just be aware that you could probably skip part E on this one and part E on that one. All right. Now, if we look up on these ones, 10.24, definitely do that at home and see if you can understand why people choke up on a baseball bat. So when you choke up on a baseball bat, you move your hands and you can think about why that affects your ability to swing the bat. So if you're into baseball, great, softball, whatever. If not, oh well, that's cool. This particular problem, it's not bad to do. The thing is, what this problem is good at, what 10.25 is good at, is seeing if you can identify the table. So for this particular problem, this is a good one. Check the units. And then, to be honest, if you can set the problem up and identify which thing in the table to use, that's the biggest part because it's non-trivial. When you look at this thing, A is whatever is sitting out in front of the X. So in this case, A, I think, would be -2. And so then you have to make sure you plug that in right and use a table right, okay? Interestingly enough, Trey is going to see this in another week or two, or maybe he already has if he's done quantum. I know you did bras and kets, but so these are the integrals that are underneath all those bras and kets, Trey. So if you did the integral formation, that's cool. 10.26. This is a great problem to get set up and see if you can do it. It surprised me a little bit. Let's see. Here's another non-uniform if you want to practice that. This was a clever variation on the wheel, 10.28. Look carefully. Let's see how this one differs. And you could see how I might mix these same exact problems up. If I put a very similar problem on the test, I might reword it this way. Okay, so the wheel has mass M, has 3 large spokes. Aha. And so in this case, this actually relates to Jay's question. In this one, M is the mass of the entire thing. So M is both the rim and the 3 spokes. And the question now becomes how much is coming from the spokes and how much is coming from the rim. So it's basically doing the same problem backwards and using, okay, so the woman knows the moment of inertia. So now she knows what I is, and she's trying to work backwards to get the different masses. So you're trying to get the different components. So basically this has mass M1 and each of these has mass M2 in here. And so you do the same exact problem as before, only you don't know these parts. And in general, people, this is a good thing to really point out. This happens all the time in physics and engineering. What you do is you work out a problem as if you know mass 1 and mass 2. And then when you get to the end, the final answer is given to you. You use your final answer to work backwards to get M1 and M2. This happens in 163 all the time, probably in 162 all the time. Okay, let me pull up the chat. Okay. Yeah, for sure, Jay, for sure. All right. Okay. All right, so that's 10.28. It's a good way to kind of see if you can just deal with the awkwardness of doing the problem backwards. You know the final answer. Can you get to the initial masses? Hey, here's the variation on that one. So this would be now take it all the way out. Okay, great. These are some kind of fun ones. So these are conceptual. And I'm going to let you do these ones at home. These are also conceptual. They could help you rank these things. That's pretty good. A common question I get every year when is it appropriate to consider a sphere as a point mass? You may have noticed that a lot of times we're like, just call it a point mass. Just call it. When can it be a point mass? If you care, do this problem. Otherwise, on the test day, if I call it a point mass, use the point mass formula. If I call it a sphere, use a sphere equation. Again, just in case there's lag. If you're curious, when does something become a point mass? Basically, you use the parallel axis theorem, and whenever the parallel axis theorem part is 99% of the total, it's basically a point mass. Okay. This is a good one. We use this later in this chapter. Definitely do 10.33 here. It's a pretty good one here. The idea is here, I total. Think to yourself, how would you handle this one? I'm going to let you read for a second so I don't just blast through this one. We're looking at I33, or sorry, 1033. Thin disk, radius r, off-axis hole of radius little r. Axis runs out of the page to the center of the disk. Center of the hole is distance x. Okay. And we've got some density. All right. So now I hope you see that this is I1 minus I2. The idea is, just like when we had center mass, you subtract the mass. Cool. Now watch out, mass 1. If you remember from the whole, mass 1 is going to be area of the solid big circle times the density, because we know that. Mass 2 is going to be area of the hole times the density. And then it's basically, you got this piece, you got this piece, you look these up in the table, you plug in this for the mass, you know the radius, it's bing, bang, bang, done. So that's enough on that. I'm going to stop for a second, see if there's any questions. Looks like you're doing all right. I'm going to get back into it. Anytime, feel free to dump them in there. Whoa. Okay, I don't know. I didn't even want to read this one. Let's see. That's cool. Okay, rank. Oh, yeah, that's kind of fun. That's more of a conceptual rank them. If you're curious, in general, the total moment of inertia can be found by adding up the moment of inertia of each subshape. So if you're wanting to know how to derive the sphere, here's one way to derive the moment of inertia of the sphere. One of the things when people do this one, they're always surprised at the result that it's 2/5. They're not sure how to get that. If you care how I got the sphere, read this page. If you don't care, if you're not a calculus freak, skip this page. Here's another way to do it. You can see I was having fun. So if you're into math, have a blast. Look at that. So this is another way to do it. So you can see that, oh my gosh. And yeah, that's plenty. We could skip. So basically, if you're working out of the book, skip pages 67 and 68, unless you want to have lots of extra math fun. Skip 67 and 68. All right. So now I want to go to page 69. This is the next big topic. It's the last topic that is covered before we get to our test 2. So I think there's energy too. So yeah, it's the second to last topic. But this is the hardest topic left. All right. Hardest topic. Whoops. Come on. All right. So if at any time you're getting bored of the slow pace, remember we are live streaming and you could go watch these later. There we go. Wait a minute. What shape am I? Oh my gosh, I'm getting lost. There we go. All right. Torque. It's a lot like force, just a lot harder. Okay. So I want to point out, notice that there are 4 different ways for us to find torque. I would love to tell you, you should only learn one of them. That's simply not true. A lot of this we will cover again in chapter 12. So in chapter 12 is really where you need to be pretty badass at this, and you need to know how to use any of these figures. So let's get into it. Torque is a cross product. So this is why we've been working on cross products, is now we can use this. So if you want, I'll show you an example where we use the wheel of pain. This way always works. If you had to know only one, it's method one. The issue becomes cross products can take a lot of time in 3 dimensions. And so it can be very, very painful to do all of your torques with method one. A lot of times, this one works all the time, and this one is a very common one. Now I want to point something out here, something that's a little bit funky. Maybe you see it. Notice something that's irritating to a physics professor in those equations. I want to point out this over here shows this is a vector, and notice over here, this is not a vector. So it turns out we will, whoops. This tells you how to get the direction. We're going to start using this right-hand rule all the time. So the issue is this. These get the direction really quickly. This one gets the magnitude and the direction. So that's why number one is the best one. All right. But here we can get just the magnitude and then use that trick down below. So the units of torque are a Newton times a meter. Look at it. It's a Newton. Whoops. Oh my gosh, I'm having trouble highlighting. It's a meter times a Newton. Why don't we say meter newtons? I don't know. We say foot pounds, but we don't say meter newtons. Nobody says joules. A Newton times a meter is a joule. Don't say joules. This is how we keep them straight. If you're talking about torques, you say Newton meters or foot pounds. If you're talking about energy, you use joules. And that's how we distinguish in energy from a torque. No, yeah. F is some force you apply. So here we go. Whoops. Usually there's something in a problem that's a pivot point. Maybe this is, I don't know, maybe it's a bolt and we're going to twist this rod around the bolt. Okay. We're going to come down here some distance and we're going to apply this force right here. So the idea is the torque will depend on all these things too. It depends on the angle that we've got right here. It depends on the distance away. It depends on the amount of force. So if you could think about this, if I'm trying to exert a torque, pretend this book is a door, right? You know that there's a hinge on the door. Right here is the axis of rotation. So here's the axis, right? And so you could apply a torque to the door, but sometimes if you apply a force, you won't. If I pull on this, it's not twisting, right? If I pull on the book or if I push on it, you have to push with some component of force perpendicular to that axis of rotation. So that's why the torque depends on the angle you push at, and that's why it's so much harder. Now, I'm going to go back to my image here because it's a little bit easier to see. The idea here is if you push at 90 degrees, you're going to get the most torque. If this angle here is 90 degrees, you're pushing perpendicular and you're going to get a lot of torque. If you're pushing right here, you get almost no torque. All right. And you could even go this another way. If I scroll down, look at this. I could literally split off the component of force that's perpendicular. This is one component of the force, and this is the other, if I could draw it right here. And notice this component right here causes no torque. It's not going to twist this thing. Remember, here's our pivot point. This component will cause a lot of torque. It will cause a lot of rotation. It's a force that causes a rotation. So it will cause torque. This one is a force that would try to twist or try to translate it, try to pull it, but it's not going to rotate it. So it causes no torque. That is reflected in the equations up here. Right here. Whoops. If I have a force component that's perpendicular, to the radius vector, I get a torque. Similarly, if I have a radius vector that's perpendicular to the force, this is a little bit goofy. Let's see what that means. Okay, you're going to hear me say this word a lot, line of action. A line of action is a line that runs through the force. Notice what's really important now. Here's where my applied force is. This is the line of action. It extends forever. R perpendicular. Sometimes you'll hear me say the words R perp. R perp. That's what I call that, R perp. That's the same thing as calling it a lever arm. R perp is the lever arm. And if you do the math, look at this thing. You draw a perpendicular bisector. What does that mean? It's a line that is perpendicular. So there's this right angle here. If I have this perpendicular bisector, that gives me the lever arm. Great. A lot of problems, this is the fastest way to go by far. Okay. So it's really important that you understand this, and you will not understand it until we do this thing. So let me clear this out, see if there's anything else I want to say. Summary, there's 4 ways to find the torque. They're outlined here. You won't really understand them until we do them. So I'll do them in a minute. These are the definitions. You can read them on your own, but do know that this R perp is a special one called the lever arm. F perp is a fancy way of saying the component of force perpendicular to R. These come up a lot. Okay. Stuff to memorize right here. This is really cool. If the line of action goes through the pivot, there's no torque. Just memorize it. If a line of action for a force goes through the pivot, no torque. That's the best way to remember that. Here's a couple of trig identities that are useful to know. In a lot of problems, we're going to see 90 minus theta appearing. 90 minus theta, 90 minus theta. Just know that anytime you have sine of 90 minus theta, that's equal to cosine theta. Memorize it. Similarly, this is really cool. Sine of 180 minus theta is also sine of theta. This is really cool because it tells us up here, this angle or this angle, you could use either one in this equation. Because sine of these, this would be 180 minus theta. Either one of those things will give you the same result for torque. So if you're not sure, do I use this angle or that angle? This is the one time in physics. Either one works. Woo! All right. Oops. Scrolling down. Let's see if there's more stuff to memorize. The sum of torque is I alpha. That's like the sum of force is mass times acceleration. Remember that I is like mass, alpha is like A, tangential, and torque is like force. Torque is a vector. Remember that direction. Normally we say counterclockwise is K hat. There's that. And then in physics class, sometimes if everything's going clockwise, we'll call clockwise the positive direction. Finally, R. What does R mean? It has a very specific meaning. Make sure you know the real meaning of R. It's not just some random radius. It's from the pivot to the point where the force is applied. So it is not, to be clear, it is not this way. That is wrong. It has to go from the pivot to the force. From the pivot to the force. One more time, from the pivot to the force. Don't screw that up. Okay. Whoops. All right. Made it through that. If you're trying to do the right-hand rule, let's practice right now. And I'm going to show you something, a trick. Take your book. Hopefully you've got it in front of you. Hopefully you can see mine here. So where is it? I can't see anything. There we go. There's my book. Okay. So now take your hand and put it on there. rotate the book to match your hand. Don't try to make your hand match the book. Rotate the piece of paper to match your hand. And so I'm looking at method 4. Take your right hand and put it on method 4. Go line your fingers up with R. So the right hand rule, start with the R vector, curl to the force vector, and notice my thumb points out of the page. R goes to F, goes to, in this case, out of the page. R goes to F, out of the page. That's K hat. Okay. So now look at this one. Okay. You got R goes to F, goes to K hat. Read the right hand rule. Take a second. I'm going to pause and make sure there's no questions on this one. See if that makes sense to you. Point the fingers of your right hand in the direction of R. Curl your fingers towards F. You might have to try it out a couple of different ways. The thumb. Oh yeah, let me show you the couple of different ways. Okay, the idea is you could go like this. Nope, nope, nope. Yep, got it. So again, nope, nope, got it. Okay. All right, enough of that. If you're curious about the cross product, it's always, this right-hand rule shows up all the time in magnetism and stuff. Look at this. It's R cross F. It's not F cross R, it's R cross F. It's always first vector goes to the second vector, thumb. So line up your fingers of your right hand with the first vector, then curl them to the second vector. The output of the cross product is aligned with your thumb. I'll check the chat. Okay. Okay, it sounds like you got it figured out there. Yeah, exactly. It's now this is a distance. This is a distance. This is a distance. This, because it has a direction, is a displacement, right? We're going from the pivot to the point, and because it's a vector, that's a displacement vector, not a distance. Hopefully that addresses that. Good questions. All right, pretty boring there. Chapter 12. I'm just going to mention this is good. Chapter 12. We use this a lot in chapter 12. Check this out. Anytime you want to, you could take this stupid force over here that's off at an angle, and it's really hard, right? Because this one has a line of action that goes right here. I could try and figure out this lever arm right here, but that's hard. That does not look easy to me. I maybe it's easy to you, but it looks like hours of geometry. So what you sometimes do, you could take any force and split it into a red force like this with this lever arm. That red force has a lever arm, R perp equals X. You could split it in, and that's this red force here. Now you could do the same thing with the blue force. You have a blue line of action, and notice R perp for that one equals Y. And so what you did is you took a complicated force and you split it into two that are much easier to work with. So this gets you the torque from that one. Now notice there's a minus sign here. You might be wondering about that minus sign. Check it with the right hand rule right now. You want practice with the right hand rule? This is it. Let's do it. Look at these two forces and verify. Let's see, I think I said this was the red one. So let's start with the red one. The red one is this term right here. Verify that this one causes a torque. This is R perpendicular. Line up your hand with R perpendicular for the red force component. Now, curl your fingers, and I see that my thumb points out of the page. I go from the pivot to the force with the right hand rule, My thumb shows. Now, if I do the blue one, notice this one would tend to twist it the other way. Think about which way this blue force would twist it. It would twist it clockwise. That's a negative k hat. The red one would tend to twist it counterclockwise. That's positive k hat. So now you know why this one here has the minus sign. All right, that's pretty cool. And I think we're about ready to cruise on. And so before I do that, I'll stop and do a quick question check. Looks like you're good. So I'm going to plow through it. Appreciate you all being here and being troopers. Let's keep going. It's one of my favorite parts of the class for some reason. I just love torque. I love center of mass. I love moment of inertia. I love torque. I love chapter 10. Chapter 10, it's just the best. All right, so here's my equation. Here's the force. All right, so there it is right there. So there's my force. Take a look. Does that make sense? It looks like it goes to the right and down, right? Cool. And then determine the R vector. So let's do this. If you want the R vector, that's it. From the pivot to the point. So you could think through that yourself. I'll write it out. Surely you can get it before I do it. It looks like 1.5 long. I'll just call that L. So it's probably L cosine theta. Oh, crap. The X component has the sine theta. Look at this. Opposite sine. So it's going to be L sine theta in the I hat. And this double check, it's going to the right. Yep. Plus L cosine in the J hat. And now I think you could plug in the numbers 1.5 and 30 degrees and hit a calculator. So that's what I was hoping you would do. And if I want to use method 1 for the torque should equal, it's not F cross R, it's R cross F. And again, F is this vector right here, or this vector right here, which has been nicely specified for us. All right. And then if you want, you could see, remember I said this method is great because it always works. It's sometimes a little time consuming. So it's also worth it to try and do this with lever arms for each component. That's basically splitting up the force into components like the last time. Now, obviously, I could do this really quickly, but I want you to have a chance to look at it. So give that a shot. I'll bring up the solutions, and I'm actually going to pause for a second so you can ask any questions you want. This is our first calculate the torque, all right? We have 2 lectures next week, and we're on our last chapter, so we're doing good. I'll get the solution. Oh, don't those look like fun? Oh, God, I love it. Oh, so juicy. All right. Whoops. What are we doing? I forgot oh, there we are. Okay. Oh, I used green and purple. Excuse me. Okay, sorry, I was a little slow there. So now let's take a look at this one, 10.36, and I show you this one. So this one is worked out in gory detail there in the solutions. I think we were up to this part. So I'm going to try and leave this all on the screen right here. And I want to just pause and see if anybody has any questions about this. So sorry if I'm going to wait a little bit. Okay. You can always tune out and go to the live stream later. We've got about another 25 minutes of class here, so I'd like to make sure you got this down. Let me get this out of the way. At any point, if you have a question, you're welcome to unmute your mic and just ask as well, okay? And then it's so weird. All right, I'm just going to wait a couple more minutes. I'll try to wait. It's so frustrating to wait because I just have no idea. So if you want, you can use the, I don't know, let's just, a couple minutes aren't going to kill us. If you finish early, go ahead to the next problem, all right? This is a fun question we're going to do today for sure. All right, so I have no idea if I gave you enough time at all, but I want to just kind of go through this while I've got you here. So this makes sense. In the problem, they said that this angle here was theta. So by alternate whatever, this is the alternate whatever is a very technical term there. That's theta. So we get this side is that, this side's that. Now, when you're doing the cross product, watch out. This is why we did all that boring chapter 3 crap. There's my R vector. Here's my F vector. When I'm doing the cross product with the wheel of pain, I ignore I cross I and J cross J. Remember, I dot I is 1. I cross I is 0. All right. And then also remember, I cross J using the wheel of pain is K. If you don't remember, here's I hat goes to J hat. This is what I mean by the wheel of pain. Goes to K hat. And you could draw other ones if you want, but whatever. I goes to J goes to K. Remember that I dot J equals 0, but I cross J is equal to K hat. So this one's pretty straightforward. It's just do the math. We did this on test something or other. I think we even did this on your test this semester. Enough on that. Moving down to the bottom one, okay? This is trying to use that new technique. So look at this one. I took the purple force here and I split it into a blue force and a red force. You're going to see me do this in solutions, I think, a couple of times. So this is a really cool trick. Now what I did is I know this blue force. Let me get my blue. Here's my blue line of action. Remember, these dotted lines here are the lines of action. This dashed line, the dashed line is the perpendicular bisector. Well, that's just the lever arm. So if I know the force component and the lever arm, that's good. So the torque for the blue one, magnitude, is this. This gives me the magnitude of the blue torque. Okay, how do I get the direction of it? Well, I go, it's hard for me to show you without being on a whiteboard, but I go upwards with my right hand, and my right hand curls to the force vector, the blue force, and I notice that that's twisting it basically clockwise. So try lining up your right hand with the screen. Line up your right hand up, curl your fingers over, your thumb points into the page. Okay. And then doing it with the red one. Oh, whoops, go back. So that's how I get the force vector right here. That's how I get the minus K hat. I did the right hand rule. Now, if we switch into red mode, well, we've got this lever arm right here. I've got this force. Here's the line of action. And so I just plug in the math to get the magnitude. Great. And then I see if I do the right hand rule, this one's not so obvious. Go from the pivot. I'm going to show you. You can always do this from the pivot all the way up to here. So you could line up your, let me clear these. You could actually go and let me do green just so it sticks out. You could take the original R vector, which was this, right? Line up your hands with the green line, then curl your fingers to the red arrow, and notice your thumb is still into the page because this green, I believe, was the R vector. So in this case, you can always use the original R vector to figure out the direction from the right hand rule. Okay. Clear all the drawings, stop, and let's go from there. I'm going to stop the share for a second. And it looks like that might be good. You're all still working. I'm going to go on. So going back to here, 10.37, this is straight up practice the right hand rule because you're not going to be good at it unless you practice it. To be clear, if you're not familiar, X means into the page. Remember we talked about that a long time ago? That's into. That's the feathers of the arrow. If I shot an arrow at you and the arrows were, so if the arrow's coming at your eyeball, you get this circle that's into, this is out of, sorry. So the dot means out of and the X means into. The feathers of the arrow going away from you as the arrow shoots into the page. All right, whatever. So there's a couple of other ones there. This is an easy one for you to do at home too as well. It's rank these things. All right. And so this gives you a chance to see how does the size of the force, the direction of the force, which ones push the direction. So these ones are really good to kind of get your conceptual down. So you should probably do these before too long. So in the next, say, 3 days, if you get a chance to lock in this torque, okay? Or maybe tomorrow morning if you want to see if you still know it. And I want to do 2 more problems and call it a day. All right. So now I'm going to look at the problems on page 71. We're finally able to do a real calculation of something. For the last few days, we've been talking about moment of inertia or rotational kinematics and blah, blah, blah. And I keep telling you this relates to like Newton's law and rotation. We could finally put it all together with 10.39. We have a uniform thin rod. It's going to rotate in a vertical circle because of this pivot right here. This pivot is green, all right? Okay, and now there's 3 forces that act on the rod. Oh, there's the rod's weight. I think you'll agree with that. And the applied force. The one that people sometimes forget is this reaction force at the pivot. All right, we really hammer that in chapter 12, but for now, let me see if this makes sense to you. Let me see if I got this in the solutions. Ooh, did I forget the ranking? Oh, there's the rankings. Okay. Wait, where's 39? Oh, there it is. I just passed it. Sorry about that. Okay, so if I could take a look at that picture, we actually have the 3 force vectors that we care about. mg coming down. Here's my force applied this way. Ooh, 90 minus theta. I got to go back and look at the picture for a second. 90 minus theta. Why is that 90 minus? Oh, okay, because this, if this is theta, this angle down here is going to be 90 minus. So again, this is theta. So that makes sense why this is 90 minus theta. Up there was theta. Got it? This was theta. Got it. Okay, and so the pivot, I claim the pivot is exerting a force off this screwball way. We will learn a lot more about this in chapter 12, but for right now, it turns out, I want you to think for a second, which of these forces are going to cause torque? So let's go back to here. Hopefully you have a picture of this now. There's mg right here. I'll color that in green. There's the force in black, and then there's, let's say, this reaction force off this way. That's my claim. Which of these forces will cause zero torque? Think to yourself. Which force causes zero torque? Hopefully you said it's R. R has a line of action which runs through the pivot. Now you could say R is at the pivot and causes no torque. You are absolutely correct. Any force at the pivot causes no torque, but it's better to get in this habit now of saying if the line of action runs through the pivot, because that will eliminate more forces than at the pivot. So remember this, if line of action through pivot, no torque. If line of action through pivot, no torque. My apologies for repeating myself a lot. Sometimes I do that because I'm never sure if the computer lags. So, and I guess I just like to babble. All right, let's go into there and see if the equation makes sense. Notice, whoops, this R term drops out, no torque. So this equation is sum of torques, and I see there's a chat. I'll work on it in a minute, or Trey, you can try to get to it. I'm trying to do this equation right now. Sum of torques equals I alpha. What I've done is I've called this the positive direction. This is being anything that's going that way, I'm calling positive. I'll catch up to the chat in just a second. So take a look. For the black force, this is the entire length. So that's why I get L. There's the force times the sine of the angle between. The angle between, in this case, is 90 minus theta. Okay. Now, and again, it's positive because it's positive. This force would tend to rotate this thing in the direction I chose to call positive. Just like in some physics problems, we call downwards positive. In this problem, I chose to call the standard math way positive. Why not start that way? Okay. Now, let's go green here. Here's mg, right? Well, in this case, that distance is L over 2. This is a right angle. So that's why I have L over 2 mg. Wait a minute. Shouldn't I have a sine 90 there? Oh my gosh. Sine of 90 degrees is 1. So you'll see that a lot. A lot of problems. If there's a 90-degree angle, you just leave out the sine theta because sine of 90 is 1. And then this is the moment of inertia. Oh, crap. I could look that up in a table. Because it's a rod at the end, if the pivot is at the end of the rod, it's 1/3. If the rod is in the middle, it would have been 1/12. How do you know? Read the table. Again, how do I know? Read the table. Doesn't look like this. Doesn't look like this. That's not it. Oh yeah, it looks like this. It's 1/3. Okay, so now after all of that, I get this. Wait a minute, how'd I get cosine in there? Oh yeah, that's that stupid thing he said I have to memorize. Remember that anytime you see this, you could replace it with this. If it helps, take a look. If you want to see that trig identity, if this is theta and this is 90 minus theta, hopefully you agree that this side over here let's say this side would be sine of 90 minus, right? Sine of 90 minus theta. Well, isn't that also cosine of theta? So just draw a right triangle if you forget that. Oh, crap. And we see that sine of 90 minus theta is equal to cosine of theta. So that's what I did right there. All right. I've got a question for you. After all this work, we figured out the moment of inertia here. We did the forces, we got all the torques, and so we got alpha. And now let's say I wanted to figure out how long it takes this thing to swing down. Well, I'm going to write something here, and I want you to tell me why this is a totally wrong thing to do. This is incorrect. You might think you could do this. I want to say, how long is it going to take to swing down? Well, how long? I'll just do 1/2 alpha t squared plus, let's see, omega initial times time. Why can I not just take this alpha and plug it in here? I'll give you a second to think about it, and then I'll check the chat. Okay, got it. Yeah, you know how it is. It's so laggy that if there's something important, I'm just going to say it multiple times. Yep. All right, here's the deal. So with this one, my question was, why can you not just take this and shove it in here? It's because this requires alpha constant. I was hoping to add a little exciting, a little exciting delay there. They say if you're a music producer, this is a random fact. If you're a music producer, sometimes what they'll do is they'll deliberately slow down the tempo of the song just before the chorus so that the chorus is hard. So then, yeah, you could do that with your physics constants too. Just say alpha equals constant. There you go. Now that nothing slams like an alpha equals constant like that. Oh boy. Anyways, I'm losing it. Okay, there's a K-hat. Great. Finally, we did some crap here. Cool. I'm going to stop the share for a second. Oh my goodness. That is what we've been trying to work up to. Now you can do a torque problem. You can do the moment of inertia to get the right-hand side. You can do a torque to get the left-hand side. And we're going to practice this on Monday and then also get into how you could redo this problem, this exact same problem, using energy, because that's another technique. Looks like there's no questions yet. So I've got the perfect question to end with today. In the spirit of true COVID toilet paper shortages, let's take a look at the bottom of page 71, problem 10.44. Whoops. There it is. Yeah. Maybe you've noticed this in real life. If you have a full roll of toilet paper, which nobody does these days, so you can't do the experiment, I know. This should have been lab this week, right? Just go to the bathroom and rip off some toilet paper. Evaluate the experience. Yeah. Anyways, if you have a full roll, think about it. What's different about the full roll versus the almost empty roll, at least in terms of moment of inertia? Hopefully you think that the one that's more full has got a greater moment of inertia, but this one is surprisingly complicated to think about. You have more mass, but you might have, yeah, right? Totally. So you have more mass, that's going to affect the friction, but will affect the friction per unit mass and things like this. So there's a number of interesting factors. If you've ever wondered why it's easy to just give a quick jerk and rip the toilet paper off when it's full, but not when it's empty, you can kind of read this one. You definitely should do problems 10.40 through 10.42. They're pretty quick. Maybe let's the fact here is if you have a disk in outer space or something, this is a great, it's a simple, like a hockey puck on a ice rink or something, basically. So we're looking down. I'm reading this question right here. I'm reading 10.40. So we have a top view. This is basically a frictionless situation. If you apply some forces, it's cool to try and do these two things, because I think if you do all three of these together as a package, they're super fast. Everything's at right angles. See that? It's either going to be like this one. This force over here clearly causes no torque, whereas this force does, and this force does. And so it just kind of forces you to see which ones are going to drop out. And like these ones, which times, like these ones both cause a torque in the same direction by the right-hand rule, whereas these ones are opposite by the right-hand rule, things like that. And so I think these simple ones are totally worth doing. They help you lock in your understanding before you get to the gnarly grinding ones. So it's really important that you do basically 10.36 through 10.42. And I think that's pretty good. And if you want a review of the angular kinematics, which is good, that 43 is pretty solid. I say we should stop there and we'll pick it up next time. All right. So I'm going to go ahead and stop the share. I'm going to stop the live stream and I'll stay online for a few